My name is Anzo Joel. I am a malware analyst and cyber defense in a cybersecurity organization. But since I'm into invention and innovation, I do believe in having general knowledge. So I do have general knowledge in other science fields like civil engineering. I told you I'm a malware analyst. For those of you who don't know what malware analysis is, in a nutshell, what we do is when, for example, a company gets hacked by hackers, I get the zero-day malware or the latest viruses, and I open them up using certain tools. For example, one of them is Ghidra, which was developed by the National Security Agency in the United States. That's the NSA, to combat cyber terrorism. I'd just like to teach you how bridges are built. I do have general knowledge in almost every science field, including civil engineering. And just like I believe that you don't have to be a certified medical doctor to have knowledge in, for example, health. Yeah. And if you're an inventor or an innovator, you need to have general knowledge in also other areas, other science fields. And I'd like us to, come up with a design for a bridge for the civil engineers. You know this. Okay. Now I know that in Africa, the education system always, has had challenges. Yeah. So in Uganda, for example, some of you have been asking questions like on YouTube and TikTok. You've been asking, saying, what was the use for us to go and learn dy, dx? Why should you find x? Find x. How does finding x benefit me today? Yeah, that's under calculus. But I can tell you that calculus is very important. Calculus is a field in science that studies motion and rates of change. Yeah, and I will tell you how this is important in different fields before we come to the main topic about the bridges. So you guys, for example, in calculus, you do things of dx dt, yeah, and you used to wonder what that's for. That's under differentiation. Then also you used to have these integral signs, yeah, the integral sign a, b. Calculus is a branch of science that studies rates of change and motion. Like I told you, we used to do calculus in high school, pure math, etc. But calculus, for example, it's so important. If only our teachers would first tell us what is important or why are we studying the things, maybe some of us would have been more passionate about engineering. Maybe you would have more engineers, but people didn't know why they had to find y or find x. So people lost hope and confidence in the whole thing. I believe we could do some revisions in our learning methods. Yeah, and so in calculus can be applied in, for example, in rocket science. In the rate at which maybe a rocket enters outer orbit, or the rate at which fuel is burnt in the rocket, or things like economics, studying inflation, the rate of inflation, and then or the rate of the, how the economy is growing. This can help you make good decisions for the nation using calculus, and other applications like in medicine, studying the growth rate of tumors. And when you're developing, let's say, some softwares that study those tumors and study the growth rate, you can determine which medicine to use and the dosage, and you become more effective in predicting the growth of the tumors and how effective new medicines are. The applications go on and on in in everyday life, the prediction of the stock markets, things like that, and many other things. Predicting the weather, whether it's going to rain or not, for helps the farmers with planting, harvest seasons, and planning properly their agricultural, settings, agricultural schemes, and everything. So calculus it helps in everyday life. And even if you're writing an algorithm, let's say to help people in agriculture or medicine or the space industry or in the stock market or in the economy, you're going to need to include some of these things, the calculus formulas, etc. Yeah. So if only the teachers told us why we were studying calculus, I think we would have more engineers. With calculus, you can predict how it's most likely to be in the next few months. or even inflation, things like that, using calculus. So calculus is very useful in many areas, and many of the softwares that people use embed many of the formulas that are used in calculus. Yeah, kudos to Isaac Newton for inventing calculus. Yeah, one of my favorite scientists and inventors. Yeah. So now I would like us to first look at a bridge. So today I would like us to consider maybe a cable stayed bridge. Yeah, there are many bridges that I can teach or demonstrate, but today let's look at the cable stayed bridge. Yeah. So we are now looking at the cable stayed bridge. We have one in Uganda, in Jinja. All right. So now, basically, when you're going to build a bridge, let me first show you. So now this would be this is the river. So this here is a river, right? This is a river, okay? And this is, let's say, the water, yeah, the water level, yeah. And so now, if you're going to build a bridge, one of the first things, of course, you have to do is to draw the plan of the bridge, and then you go do surveys on the area. You know, the location of the bridge, the purpose of the bridge, its environmental impacts, yeah, and effects. You have to take into account the environment as well. You have to do soil sampling, soil testing on the soil that is on the site. And after you do all that, with your plans, you have all the simulations ready, then you might be able to, of course, now to proceed with the permits and you know, the endorsements from the government. When they give you permission now, let's say, to construct a cable stayed bridge, then you come and you start clearing vegetation on these sites and removing every debris. Then after that, we're now going to be building the bridge piers. We're going to have 2 bridge piers here, and I shall come back to these abutments later. So now, normally, if let's say I'm not going in order, but let's just begin with the bridge piers. So for demonstration, let's begin with the 1 bridge pier. So normally you're going to have a cofferdam. You build a cofferdam here. So a cofferdam, you basically put piles into the water, pile sheets, and they have to go deep into the bedrock. And then you drain the water out. Yeah, you drain this water out. Once you're done draining this water out, of course, you have your pile sheets here to keep the water from coming in, yeah, into the bridge piers. And then you, of course, you have to do some soil testing here because the soil here will be weak. Then you use some excavators to remove out the mud and the weak soil. And then you can do like some cone penetration testing to test for the strength of the soil here and to find the bedrock. So you drill until you find the bedrock. Once you find the bedrock, now the bedrock is where the foundation of the bridge pier should sit, yeah. And then after that, you now pour your concrete. This is where the concrete can go. And then, of course, now you come. Of course, you also put your more piles here. But you drill this, they have to go down into the bedrock because the bedrock, the whole pier has to be firm. So for it to be so firm, it has to be well connected to the bedrock. Because as you're building your bridge, you need to take into account fluid mechanics, yeah, all those forces like hydrostatic pressure, you know, all those buoyancy forces, drag, etc., and other loads like wind loads, seismic loads in case it's an earthquake-prone region like Japan, yeah. So after that, you now come. The next step is to use strong materials to start building your bridge pier right here. So now this bridge pier goes now here. This is where we're going to put stay cables, okay, this pylon. So now basically we are going to now start installing our deck. But before we come to the decks, of course, here you all know you have to start with the foundation here. After clearing the vegetation and grading and everything, you now build your foundation here, connected to the bedrock with several courses with different materials, either geosynthetics or concrete or whatever, to reinforce these foundations for your abutments, right? Now you have your abutments this side, and then now we are going to install our decks. So these decks normally are prefabricated off-site, probably, maybe in some factory or warehouse or something, and then they are lifted using cranes, and then assembled in place, and then they connect. You assemble the next, you connect the cable, the stay cable. Then these stay cables are made of steel, very strong steel, and each cable has tiny, strong steel wires, and then you combine many of them together, so they are very, very strong and stable. So basically, what you see this side is also what you repeat this side, but you have to go, as you go this way, you go this way as well, so the bridge pair doesn't topple off. Yeah. So then, of course, you connect it to your abutment. Then after that, when you're done, you now go into the next phase, which is of course making the road smooth, and then coming into testing. You're testing the road inspection, yeah, inspecting the road for quality control, so that the bridge and the road meets international engineering standards. You want your bridge to last for 100 years and more, yeah. Not the bridges that some people build, and when the rain comes, the rain flows, washes it away. After every few months or every few years, the bridge is washed away by all the forces of drag and all those things of fluid mechanics, etc. So you want to make sure you take into account all that. So after that, the inspection is done, then you do load testing. So typically, the way load testing is done, you get so many heavy trucks, very, very heavy trucks that are fully loaded with probably thousands and thousands of tons or kilograms of weight, and you pack those trucks back to back, bumper to bumper. You pack them on the bridge. Okay, I'm using one bridge pier just for demonstration purposes, but the state cable bridge, for example, in Jinja, you'd have 2 bridge piers, yeah? So this is just for demonstration purposes. This is a basic design. And then once it passes the load test, and then you're ready to open the road, you call either the president or any dignitary to come and open the bridge to the public, etc. When they were constructing the bridge in Jinja, I was there, and as one of the engineers who was on site taught me some of the things in bridge construction, and I know a lot about bridge construction, but I also did my own research to fill in the gaps of the things that I didn't see. But I saw a lot of the things that they were doing at the bridge in Jinja, on Alubade Dam.